Good morning. So it's time to start, and today we have yet another change of the topic. From quantum dots, we go to qubits, elementary units for quantum information processing. And what is the plan? We look first at general principles of quantum information processing as they are seen now. We will talk about quantum computer requirements to quantum computer, a paper quantum computer, how it is supposed to work. A large chunk will be about quantum manipulation, about manipulating wave function, arranging qubits in configurations which are useful for quantum information processing, how to make it using resonances, how to provide single qubit operations, and quantum gates. Those are operations involving many qubits which are necessary for quantum computation. Then we look at concrete physical realizations of the qubits. Mostly, we will talk about Josephson qubits, which explore homemade quantum mechanics made of combination of Coulomb blockade and Josephson energy, Josephson effect. There are many possible qubit realizations which have been put into practice, have been experimentally realized in different time moments. At the moment, it looks like the last one, transmon configuration, is the most practical and modern Josephson qubit schemes generally implement transmons, but it's also fun from physical point of view to go through all different realizations just to understand how you could make a qubit from eventually any quantum system. And I will address a spin qubit shortly. So both Josephson qubits and spin qubits are under active consideration in experimental groups here in Delft. So that will be a short introduction to their activities. Very good. So let me proceed and let me just start. There is a description of a qubit and why it can be ever useful in comparison with what we apply very well every day, every second of our life, in comparison with classical bits, classical information processing. All right, let us understand the difference. Simultaneously trying to present it on the same background. Classical logics. All computers, all information processing at classical level is based on, in fact, two-level systems. Classical bits. And these two-level systems can be in two states, either 0 or 1. It's real classical state, so it's either in 0 or in 1. You can switch between those, but it's what you have in classical system. And with this, we can do much. We can process information quite efficiently for our modern purposes. As far as quantum logic is concerned, it's also qubit is also a two-level system, but it's quantum mechanical. What does it mean? It doesn't have to be in one of the states, 0 or 1. It can be in an arbitrary linear superposition of the states with coefficients alpha and beta, which in terms of computers are floating point numbers, eventually continuous numbers. Yeah, normalization imposes this condition on the qubits. Wave function has to be normalized. Also, the total phase of wave function usually doesn't matter. That leaves us with two dimensions. So instead of two states with possibilities to classical states 0 and 1, we will have continuous manifold of the states, two-dimensional manifold. Right. Let us understand the biggest differences in eventual number of possible states. For a single qubit, it doesn't matter much eventually. It is all about scaling of number of possible states with number of qubits in that. Good. So if single classical bit can be into states, there are 2 to the power n available for this operation. It's eventually a lot. So many combinations you can make just with 8 classical qubits, with 64 classical qubits. You could eventually present any floating point number with high accuracy, so it's almost continuous. It's a bell by itself. What will happen if we take n quantum bits and qubits? In this case, you will have 2 to the power n dimensional space of wave functions. All right, to change dimensions into number of states available, let us evaluate how many classical bits we need to present the state of n qubits. Let us see. We have, let us take 64 classical qubits to represent a floating point number. And we have to the power n dimensions, which means that we have to the power n times 64 bits to represent n qubits. That's really enormous, right? So the number of classical bits in modern computer, I guess it would be like 10 to the 12. Yeah, something like that. And that would implies that you can, with a peak model computer, we can only represent, let us see, eight qubits. And suppose we can just use the wave function of qubits for memory. It means that for a given number of quantum bits, we have that much memory, and that's enormous. With 40 qubits, you could represent all musics which have been ever played in the whole world since invention of music. It's a simple, perhaps naive algebra of 2 to the power n, but yeah, it shows it shows how rich could be quantum applications. However, let us understand the drawback of it. If we talk about wealth of memory, it is something, some information which we have put into wave function. Right, so if we read that, we necessarily collapse wave function, which means that we don't have any reliable way to read what we have put into this system of qubits. Due to, again, quantum mechanics gives us this wealth, and it looks like it immediately takes it back because of the fact that quantum wave function cannot be just measured in one shot, can be just categorized in one shot, and one cannot do this in many shots because information is lost. So that's actually not why quantum information processing is so popular nowadays. It is not that wealth of memory. The real interest to quantum computation came when people recognized rather simple property, and they had rather simple idea. It was difficult to express it mathematically, but the idea, in fact, is rather simple. In order to process information, you don't have to read it at each stage of processing. This is how how classical computer works. That's pretty well corresponds to our everyday experience with manipulating classical object, but it becomes crucial for quantum computations. So, in fact, in the process of quantum information processing, which can be very complex, very involved, quantum computer doesn't have to be in a certain state, does not have to be read, and it can be read. Information from quantum computer can be extracted only at the end of computation. Right. When people recognize this, they could find several algorithms where you can prove mathematically that quantum computer can perform much better than the classical one. First example concerned encryption. It was about representation of big numbers in terms of it was a factorization of big numbers representing a number as a product of prime numbers. Very good. So that procedure is known to be very slow and inefficient for classical computer. It can be done much faster with quantum computer. There are several other examples. I stress that not every algorithm on quantum level will perform better than at classical level. But there is a set of algorithms which make this implementation practical. Right. The most kind of, yes, it's requires frequently lots of math to understand why one algorithm, just to estimate how an algorithm performs better or not. If we just regard it as physicists, we can still find rather obvious practical implementation of quantum computer, namely the simulation of quantum systems, right? A usual example is that we want to develop a new drug, and it's a molecule consisting of a certain number of electron states per atom. There are many atoms, so the wave function becomes very complex and cannot be put into our usual computer. We don't have that many classical bits for that, but we can simulate this molecule with the same or comparable number of qubits. All right, that was the story about why quantum information processing is of any interest. If you have any questions, please don't forget to use chat, or you could just speak up. Right. So the discovery, mathematical discovery, has happened in the beginning of 90s. So it is about 30 years ago. And it gave rise to the whole revolution when people tried to put quantum bits into practice to realize it in hardware. As to software, the paradigm of quantum computer, kind of paper quantum computer, has been set very quickly, and it exists already for about 30 years. So what is that about? How does it work? It's best to look at quantum computer as a process. So that will be timeline. And that funny symbols are operations which are executed on wave function of quantum computer. Right, so what you see these operations. It's a program. It's supposed to be executed on quantum computer. Right. So these horizontal lines, they indicate individual units, qubits, individual elements of this quantum computer. And the first stage is to prepare these qubits in a certain state with a certain wave function. Then we apply all other operations. So look, these operations only affect corresponding qubits. This operation, as the symbol suggests, I'm sorry, as the symbol suggests, affects two qubits. This operation actually shows that the state of this qubit is affected by the state of all these three qubits. So there are different elementary operations, guides. It is essential that quantum coherence is kept. So there is wave function before the operation, wave function after operation, which means, according to laws of quantum mechanics, that any operation can be presented as a unitary operation, a big unitary matrix which connects these two functions. Yeah, very good. So in the end, we still want to receive some information, this quantum computer. So this is read out of resulting wave function. As we discussed, the information can be just obtained in one shot in the course of single measurement. What one can do, one can prepare the wave function again, run the same program, measure the result. So one can collect statistics, thereby one can eventually characterize the whole wave function we would like to compute. So usually single execution of quantum program is not enough, since we want to characterize a wave function. We run the same program many times and collect statistics of the results. All right, that's paper quantum computer, how it's supposed to work. From mathematical point of view, it's just multiplication of different unitary matrices which involve single qubits, many qubits, so on. All right, so how to put it into practice? For that, there has been several criteria formulated. Some of them are obvious, some of them are less obvious. Let me go through all of them. So, 5 De Vincenzo criteria. First of all, we need to make qubits. We'd like to physically realize two-level systems where we can store quantum information, where we can keep the wave function. Second, we need to operate the qubits. We want to change the wave function in a way we'd like to do. We have to do it with single qubits and also with several qubits. They say that in principle, operation of two qubits, two arbitrary qubits in quantum computer would do so. But in any case, it is about changing the wave function. Right, so after that, we want to read quantum information. Yeah, remember it is statistical, so we have to think about efficiency of readout and ability to repeat it many, many times. Yeah, but that criteria are rather trivial. Most important criterion is that of weak decoherence. What does it mean? We want to keep wave function of a number of qubits in quantum computer absolutely intact, so that it obeys the laws of quantum mechanics. In reality, these qubits interact with environment, interact with all the billions and zillions of other quantum degrees of freedom. And in fact, information leaks from quantum computer, and one has to do something with that. One has to reduce the interaction between bits of the computer and the rest of the world to really be sure that quantum computer processes information without errors. Right, one doesn't have to keep this decoherence all the time. One needs to keep it only during the computation. After you read information, then yeah, it doesn't matter if quantum decoherence has been taken place. Right, that appears to be most challenging criterion to fulfill, and most of quantum technologies combat this coherence. Another less obvious criterion is the scalability, which is in this context. Let's not go into details. It is about providing possibilities to put many qubits working together. Otherwise, one qubit is interesting in physical system, but it would never provide us real applications where quantum computations will become better than classical ones. So one has to develop such quantum computing schemes which allow integration of many qubits within the same quantum computer. Okay, that are criteria, and they also emerge very quickly. And there was long experimental work and engineering work to make it practical, to make practical devices satisfying these criteria. To some extent, number of qubits working together is the most important criterion for realization of quantum computer, for kind of to tell whether quantum computer is good, powerful, or not. Usually, it's not about speed of computation, and there are issues with the speed to make it to combat the coherence, which should take some time. Interaction with real world, with external world should take some time to be realized. So in this case, it's better to perform quantum processing as fast as possible. However, cannot do it very fast because representation of the qubit doesn't work if you did fast. So instead of two states of a certain quantum system, you assess very many all possible states. Um, right, that means that your quantum computer does not work as intended. Okay, any questions so far? Then perhaps it's time to talk about timeframes. That was 30 years ago, and in the last, say, 10 years, we have very much money pumped into quantum processing. Important players, companies like Google are interested in realization of quantum computer. It develops very fast, and we cannot say at which stage it will stabilize, at which stage it will become real commercial product accessible for large audiences, for big applications. It's on the move. Time frames are not known. In order to give an example of time frame, usually at this stage I recall the history of classical computer. Right. The classical computer, with many, many details which have been realized in centuries and that are still in the base of any quantum computer architecture. All that has been done by British gentleman, son of banker, Charles Babbage, and that was in 1822. Steam engine, steam epoch, steam age. Right, so it might be just, one could say, it was perhaps just stray idea, something on paper which nobody needed. That's why it didn't go that fast into practice. No, that's not true. Charles Babbage got grants from British Navy, from Minister of Defense, because fast computations have been required about the time. And he really got practical. He got blueprints of computers. That time there have been no electronics, of course. So these computers have been mechanical. Right. So, but they would be computers which would operate pretty much like modern computers too. But in practice, as we know, it took much more time to realize practical classical computer like it appeared somewhere about this year, but that was a large room full of electronics for a single computer, and it became kind of readily available only in 150 years after discovery of Charles Babbage. That gives us an example of framework, and actually my idea is that for having quantum computer in every household, we would need about that much time. That's not reason not to work on it, not to investigate how quantum computations work, quantum information processing work. Okay, that was a general part of my lecture. Let's see how I'm doing. I could do better, so let me perhaps accelerate a bit. And let me talk about simple but astonishing fact. In fact, if we really talk about the qubit, about quantum system which consists of two levels, we don't have to think much about how we made it. Well, we've seen quite some universalities in quantum transport already. Quantum point contact, with the same conductor, same number of channels one can make from many materials, semiconductors, superconductors, coupled, whatever. It remains the same. The same about qubits. Whatever you make it with, it will be described by two-component wave function. Two-component wave function necessarily implies that the Hamiltonian, which governs time dynamics of this function, is a 2-by-2 matrix. Right. In all textbooks, an analogy with simplest system, an electron spin in magnetic field, has been used to illustrate this 2-by-2 Hamiltonians. And that's why the components of this Hamiltonian are sometimes called as fields, magnetic fields. Right, so let us recall simple mathematical fact that each 2-by-2 matrix is a linear superposition of 4 possible matrices. Matrix which is proportional to unit. The matrix is usually not really required because it just changes the total phase of the wave function. So that's why we are left with 3 components characterizing this Hamiltonian, which one can present again in terms of Pauli matrices, which has been discovered and introduced in the context of spin physics. So any Hamiltonian can be seen as consisting of 3 fields corresponding to 3 different Pauli matrices. Those are parameters we can change in time and thereby change wave function. Let me talk a bit about convenient representation of wave function, visual representation and mathematical representation, which comes very handy when we talk about qubits. All right, so it's a representation of a Bloch sphere. Bloch is then, sphere is here. So there's a unit radius sphere in 3-dimensional space. We have 2 states in the qubit, 0 and 1. And these states correspond to opposite points of the sphere in one of the directions. Let's choose convenient axis. Let's take z-axis in such a way that north pole and south pole of the sphere correspond to these two states. How about the rest? Let's now recall that wave function is a superposition of these two states. And let us have a vector of coefficients of the superposition. These two numbers. And let's associate these coefficients with angles in spherical coordinate system, angle theta, angle phi. All right. What we write here doesn't really rings a bell. What would ring the bell if we just take the wave function and compute average components of spin? For this quantity, we have usual representation of a unit vector in spherical coordinates. So that will be z component and it will be x and y component of this vector. So spin corresponding to this wave function has a comprehensive expression. Right, so if we have a function, this points us here, we can immediately see what is spin direction, average spin direction corresponding to this wave function. As to these coefficients, A and B, they are given by that. Okay, so that's block sphere representation. Wave function can be here at south pole, can be, north pole, can be here in opposite state as a south pole, but it also can be, for instance, at the equator. What is the equator? It's equal weight superposition. So modulus alpha, modulus beta would be 1 square root over 2, chances 1/2, which still be characterized by a phase by x and y components. They can be completely different in this state. So all equal weight superpositions are there at the equator. Good, that was block sphere representation. Let us perhaps make a short break, 5 minutes break, and then I will go further. Good, so we have been talking about block sphere, convenient visualization, representation of a single qubit wave function. Yeah, we can immediately see that in fact it's a family, continuous family of possible wave functions. And yeah, these two states, working states or qubit, are only points in the space of these wave functions. Let us see, let us discuss what we can do with these qubits, how we can manipulate these qubits. Before any manipulation, we need to um, make sure that we know the initial state of the qubit. Otherwise, the computation would be senseless because we don't know what we start with. Right. Preparation of the qubit is usually taken in a very simple fashion. Right. We just have to wait. We just have to allow interaction with outside world to thermalize the state of the qubit. Um, Suppose we have a Hamiltonian where field B is along Z. Then we have two states, two eigenstates of the Hamiltonian: ground state and excited state. And if you wait for a long time, for sufficiently long time, we will find the qubit as in the ground state, provided the temperature is sufficiently small, much smaller than the energy splitting between these two states. Right. For modern quantum computation schemes, it is not enough. So modern schemes try to accelerate this process and also do some manipulation, just prepare computer in initial state, but letting quantum computer to relax is the most obvious way to prepare it in a given state. Fine. What will happen next? We want to change wave function. We want to put it in a certain state. Let us first talk about pulses of a field in a certain direction. So at the moment we could put all fields to zero, no Hamiltonian at all, so wave function is supposed to be stationary. Right, and then we will apply a pulse in x direction. So what does it mean? For some time tau, the value of bx won't be zero. What will happen in this case? Well, magnetic field supposed to rotate spin. So in this case, the spin of wave function will be rotated about x-axis on a certain angle, which depends both on intensity of the field in the pulse and on the duration of the pulse. So it takes some time to rotate the field at given x. Right, so how can it be written down in terms of unitary matrix? It's a rotation matrix corresponding to the angle gamma, which can be explicitly written in this way. So any initial wave function can take alpha, beta, multiply it with this matrix. We will got the result in wave function. Simplest example, if the qubit is again in ground state, that's the result. That's the result. Let us understand it for specific values of this angle gamma. If we start with whatever the state, south pole and north pole, 0 and 1, and rotated by 90 degrees, we got at the equator, right? So it's linear superposition with equal weight. If you rotate the spin by pi, we just make spin flip. If we were at 1, we go to 0. If we were at 0, we are at 1. So it's spin flip operation, which corresponds to not operation, negation operation in classical computers. Good. What will happen if gamma is 2 pi? In this case, the direction of spin is the same. So first simple idea is to say that wave function is the same. However, and it's a fundamental property of dimensional wave functions, it is not the same. If we rotate wave function by the angle of 2 pi, it will change sign. This sign does not affect the components of spin, but it is there. You can interfere with another function. You can with wave function of yet another system. Right? You could detect this change of sign. And only if you rotate it by 4 pi, you got precisely the same wave function. The sign change is compensated. Right. So there are examples, simple examples of quantum manipulation. At the moment we do it very simply. We could switch off all fields. We could just give pulses of the fields during time, and we could certain time, and we can rotate effective spin around any axis. We could visualize the result in Bloch sphere. There is also a rotation which would not do much with basic states 0, 1, right? So if the spin is rotated along that axis, and if it's initially in 1 or 0, right, nothing will change. Nothing, no, it's not quite true. There will be some phase shift acquired, right? It can be implemented in the same way. This phase shift operator, you apply field in that direction now for a given time, you make this phase shift. Here, if spin is not precisely in 1 or 2, then it will change its position in Bloch sphere. In 1, 2, it just acquires phase shift, but it's also legible operation which affects the work of qubit. Good. This simple scheme would be perfect if we really had the ability to switch off all these components of effective magnetic fields. Frequently, this possibility is absent. Right. We use as two states of the qubit the states which are split in energy. How one can model it? Well, we just have some field in direction that say, and that can be cancelled, can be quenched without destroying the qubit. The question is how, if we can still provide quantum manipulation, and the answer to this question has been known for a long time. It is resonant manipulation, which is readily applied for large ensembles of two-level system spins, like in nuclear resonance tomography, in medical applications. but can be also implied to a single qubit. Let me understand how it is done. The idea is to still implement pulses, but it won't be pulses of static field. Rather, there will be pulses of the field which oscillates at specific frequency, matching this separation between the levels in the qubit. Right, so this is this resonant field applied. Okay, Z direction is fixed, so we apply it in X and Y direction. You see that it oscillates. How to understand how does it work mathematically? Well, it is a transformation of tiny pattern Schrödinger equation described in the qubit into rotating frame. If we consider a function which oscillates, which rotates about that axis with this frequency, right? In this system of coordinates, there's no BZ field. It is cancelled. And the oscillating field in this system of coordinates in rotating frame becomes constant field. And we are back into previous scheme. We are back to the scheme is statical pulses. All right, so that explains rotating frame, that explains resonant manipulation of the qubits, which is still the most widespread way to operate single qubits. Let me talk about quantum gates. It's a bit, it's not such a self-explaining term. It is taken from classical computers. And as far as quantum gates are concerned, it's a unitary operation. It's operation on wave function, which involves n qubits. One cannot make quantum computer just rotating individual qubits, because in that case it will be n very small quantum computers, and we can never harness the power of quantum computation. This n qubits won't work as fun. However, it can be kind of proven that simplest gates, which involves only 2 qubits, which is called C0, can be used as base elements, and combining C0 and for different qubits and single qubit operations, one can build a universal quantum computer. One can provide arbitrary quantum program which can be executed at this quantum computer. Very good. So let me concentrate on this C0 gate. Let me understand what does it do. In distinction from many quantum gates, it has also obvious classical analogy. Right, what does it mean? It operates on the second qubit. It changes only from 2 qubits, it changes only the state of the second qubit. And but the result of this, that the fact whether the state is changed depends on the state of the first qubit, control qubit. Right, and if control qubit is in state 1, the second qubit flips, and it doesn't flip if it is in the state 0. Good. How to express it mathematically? First, let us understand how wave functions would change, what we wanted to change. Right. 0, control qubit is 0. Nothing happens with the second qubit. Control qubit is 1. Here, this 2. So there is a flip of the second qubit. If we express these relations in matrix form, we end up with this matrix of C0, unitary matrix. Fine, so much interest to C0 is theoretical proof that it is with C0 one can make arbitrary quantum algorithm for any quantum computer. It doesn't mean that for practical implementation one has to use C0, but at least if you can make C0, you're in the business. Let us see. Let us first understand how we can provide interaction between 2 qubits, which is necessary for C0. Let us consider simplest Hamiltonian, which involves spin-Pauli matrices of 2 qubits. It can also be represented as a certain number of fields, which provides pairwise couplings of all qubits or owing to symmetry of this matrix, three matrix. We have 6 independent fields in this context. Right, let us give an example which will realize quantum gate in this context. Let us take 2 qubits, and for instance, one can realize the following interaction between this qubit, which is characterized by constant. And suppose we can play with this constant, we can switch interaction off and switch it on, given certain value to this j. Pretty much the same way as we did with the fields, the 3 fields of a single qubit. Good. So we assume interaction is like this, and we give a pulse of the field, and we see the result of unitary operation. It is not C0 we are after at any value of rotation angle. It still differs from C0. But we have already provided interaction of 2 qubits, and we can, in principle, make a C0 operation. And this is a matter of programming, matter of multiplication of different matrices to get the desired result. That's the realization of C0. Which involves single qubit operations, and those are rotation of qubit 2 at different angles, which involves this pulse of interaction between two qubits and also several single qubit rotations, and that all together that will give the desired transformation C naught. So it's a matter of programming how to make from elementary unitary operations a unitary operation, unitary matrix, which you want. All right, that was about abstract qubits, and we still have like half an hour to talk about physical realizations. Fine. Again, as I promised, I will concentrate from all plenty possibilization of qubits, which will also involve all atoms, whatever. We just concentrate on the realizations which involve solid state and which are worked on in Delft. Those are Josephson qubits. Now research is concentrated on transmit qubits, but yeah, all these earlier designs are also fun to discuss and to understand how quantum engineering actually proceeds, how one can think of quantum systems in engineering terms. And yeah, shortly, if time allows, I will talk about about spin qubits. All right, let me talk about Josephson. Let me first refresh Josephson quantum mechanics, which we discuss in lecture number 7, I believe. So a single Josephson contact can be seen as a quantum system with a Hamiltonian, and one can treat this Hamiltonian in two representations. One can look at the wave function as a function of phase, superconducting phase, Josephson contact. Then the Josephson energy looks like a potential energy, and Coulomb energy looks like kinetic energy in this quantum operator. So it's like a particle in parabolic potential. One can use alternatively the charge representation, which is sorry, more convenient. So in this representation, Coulomb energy is diagonal, while Josephson energy corresponds to shift of number of charges by 2, corresponds to Cooper pair transfer through Josephson junction. This Schrödinger equation has to be supplemented with boundary conditions. So as wave function is periodic in phase, and then we have single Josephson island. The charge is discrete, or it doesn't have to be periodic, and then we deal with a single junction between two leads as it is given in the plot. Right, so combining Josephson effect and Coulomb blockade, we can build quantum systems. Let us see how to make qubits, how to simplify those to qubits or given a choice of parameters. We still have plenty of parameters to choose, and the most obvious choice is the relative strengths of Coulomb and Johnson energy. Let me first talk about charge qubit. And in charge qubit, charging energy dominates. So in fact, the states are almost classical charge states. They will become quantum mechanical, as we shortly discuss in lecture number 7, close to level crossing, where the energies of two charging states are degenerate. So small Josephson energy can do its work, can make quantum superpositions of these two states, equal weight superpositions, which occur precisely at the point of formal degeneracy. That's level splitting induced by Johnson energy level splitting small. Right, so that is indeed two-level system, a qubit, charge qubit. And that was eventually the first Johnson qubit, which has been realized now more than 20 years ago. How it has been made, let me just try to concentrate on concrete experiment on a concrete device which provides everything that we need, including the readout. So how this has been made. Right, first of all, there was Cooper box island. Here's the island. It looks pretty long, but it's still an island, long island, so to say. So when we can store discrete charges, this is Josephson reservoir for it in this loop. If one changes magnetic field in this loop, one can modulate Josephson energy. That was the idea to have a look here. The charge state, as you see, further can be probed, well, basically by putting charges into this probe electrode. What else? There was also a gate for manipulation of this box. And as we see, it is electrostatic modulation. So it was just the gate modulation of gate potential. All right, so that's the scheme. Let us see how it was manipulated. Best way to do this is to look at this plot. Right. This plot shows the energy levels near crossing which we described. Right. And this axis is the gate voltage, so one can go closer to the crossing to avoid the crossing or go farther from it. If you're farther away, we have almost pure charging state. And the probe is tuned in such a way that if you wait long for the state, you're sure that the island is the ground state. The island is here. Then they do the following very simple manipulation. They change gate voltage in such a way that it gets immediately to this point and wait for a certain time. And after that, they get it back. So what will happen after this? The split in Johnson energy would result in rotation, about x-axis as we see in our example of manipulation. Right. After the pulse, we are here. How to read the resulting state? It is important that if the system is in high state, it gives electron into the probe. And if it's in low state, it does not. What does it mean? It means that if you measure the current in the probe, we can understand what is the probability to be in the state in these two states for a wave function. This probability is a result of manipulation, so it depends on the angle at which the wave function is rotated with its pulse. Right, and that's experimental data, which wasn't very perfect as it supposed to be for a pioneer experiment. So it is a current for a long sequence of pulses, or it was periodic pulses, and this current exhibited oscillations as a function of duration of individual pulse, as a function of rotation. So that proved quantum coherence. That was charge qubit. And what I want to say, of course, it was very good for demonstration. The qubit was natural, involving only two states, but it was not good for practical purposes. And the reason it didn't go, it is enormous charge, noise in the systems, in block systems, the potentials of islands are affected by background charges in the substrate. One can, in principle, tune it for every given experiment, but the charges move. And shortly, charge noise is too big, and it provides fast decoherence of the states of charge qubits. So, although it was good for illustration, it was not good for practical reasons, and there were attempts to change the qubit design to make it better. Alternative design. Also very simple, very different region of parameters, very big value of Josephson energy, single junction. In that case, let me, to understand how does it work, let me recall, how do you call it, Washburn potential we've been talking about. Washburn potential for Josephson junction. And the parameters were tuned in such a way that the current was close to critical. And one could just concentrate on a region of phase which is close to critical value, where it becomes a cubic parabola potential. If one consider quantization of this cubic parabola potential, one can see several states, and this 0 and 1 have been used as qubit states. It's a matter of choice, right? Eventually, any two states from a set can be used as a qubit state. Why it was especially interesting, we will see it in a second, for when we discuss the manipulation and breakdown. Good. First, manipulation. We understand that in course of preparation, the system is in this state. How to rotate it? Or we could just apply a pulse of oscillating current with a frequency which matches the frequency between 0 and 1. Okay, we apply resonant pulse. The qubit would go to superposition of 0 and 1. How to check it, how to read out the qubit. All right, there was an interesting engineering trick for that. To read out, the authors provide microwave pulse which is resonant between this first and second level. Second level is very close to the edge of the potential. That's why tunneling from the second level to that side is reasonably quick, much faster than the tunnel from 0 and 1. Okay, it tunneled, and right, if you remember word bond potential, it means that it provides a motion of Josephson phase in this direction. So it provides, in fact, a voltage pulse which can be detected. So in this way, one can figure out what is the probability to be in the state 1. After manipulation, one can see where the qubit works. Okay, it's been working. Yet another realization. That is realization with a single junction, and yeah, the idea can be best explained if we talk about linear inductance, linear inductive loop, which encloses this junction. If you look at energy of this junction as a function of phase, what do we have? We have cosine term, and we have parabolic term. The coefficients in these terms depend on those energies and inductances, and what would be a good choice. Josephson energy goes like this, and the inductive energy applies parabolic background to this. And let us tune the coefficient, the curvature of the parabola in such a way that it compensates negative curvature here at this point. Okay, this is function of flux. This is flux pi. Right. What kind of potential we will encounter there? Eventually, it will be two-level potential. Sorry, a potential with two wells. If the compensation of two inductances is exact, it would be just 5/4 potential. If it's not exactly compensated, then we have this small barrier between two wells. All right, and there are quantization in these two wells, and we have eventual literal realization of the qubit, which we discussed several times in advanced quantum mechanics, a particle in two wells, which can be on the left and on the right. All right, it has been made in practice. It was also research in Delft. In fact, inductors are not very technological, but the inductive loop can be represented with two Josephson junctions. So the resulting device, in fact, involved three Josephson junctions in a loop. Right, it has been also realized about 20 years ago, and it had much better parameters with respect to decoherence and which is the most important property of qubit. The states, basis states of a qubit corresponded to different rotations of persistent current in this loop, either in that direction, let it be 0, or in opposite direction, which is state 1. Fine. Transmon qubits. Which has been invented and proposed shortly afterwards. What was the main idea? The main idea was to put paper box, a Josephson junction, with an island into an environment which allows easy manipulation and easy readout of the qubit. And this is environment of a cavity or transmission line, which has some resonant frequencies, which are close to resonant frequencies of the qubit. The heart of the transmon, this Josephson junction, was it's again Josephson junction, but the ratio of Josephson and charging energy would be around 50. What does it mean? It means that the Josephson energy dominates, charging energy is small, so it provides quantization in a cosine-like potential. And right here, it's those are quantized states in this potential, which is, I guess, close to actual transmitted states. Right. As we see, first states are very close to those of an oscillator. So in fact, the resulting system is just slightly non-linear oscillator. The difference of energy difference, say, between this pair of levels and this pair of levels is just 10%. But due to cavity environment, due to the fact that resonant frequencies are pretty well defined, it is enough for all possible quantum manipulations. Right, so transmontans comes from the fact that it's in transmission line, and in fact, to improve on noise properties, big Johnson energy is a must. So it is just slightly nonlinear oscillator. This realization seems to be leading at the moment in corresponding research. Right, that was, for instance, realization of 2-qubit processor in 2008, which quickly became 3-qubit processor. And yet, several years it became already subject of intense technological development. And there were 1650 3-qubits. I didn't look at the last updates, but okay, this research is involved, is evolving. Sorry, and yeah, it requires more and more brains, more and more money, and it goes on, but it becomes also very applied and. From my point of view, from point of fundamental physics, rather boring, to put it frankly. Let me use just to say a couple of words about spin qubits. Right, the idea of spin qubits is very simple. We just use the property of an electron to be into two states, so it's natural. Each electron is a natural qubit. Right. What one could do with this, one could just put electrons, single electrons, one electron in each dot, and manipulate their spin. Actually, with pulses of electromagnetic field, magnetic field, or electric field, one can energize these qubits, rotate these qubits. For this geometry, one can also modulate this gate and modulate the interaction between these spins. And in this way, one can provide all this computer paradigms. That's one of the devices which has been used for these purposes for demonstration of spin qubits. Again, it should provide something more single qubits. So there were 2 qubits corresponding to these 2 dots. And again, the resonant manipulation in combination with tunable barrier and in combination with readout of spin which, to give a detail, speed has been transferred to charge. So depending on spin configuration, the charge in this dot can be either 1 or 0, and that can be read with, we discuss it for quantum dots, with a quantum point contact which is nearby the dot. Right, I guess that's what I wanted to say about spin qubits. So let me finish my lecture. Thank you for your attention. I will see you next time, already offline. So.